Okay, hi, Assalamualaikum warahmatullahi wabarakatuh, and a good day. So, today we continue our topic on the DC drive. So, according to the previous topic for the DC motor, so I hope all of you already done the revision, okay, done the revision for the previous part, which is the type of the DC motor and how it's work and how to control the speed. So, according to the previous one, so we will cover more detail on this. Okay, so actually for this topic, for this chapter, the content of this chapter, we have solid state control of separately excited DC motor, and then the single phase half wave drive and full wave drive, and then the continuous aperture currents, and then the effect of the freewheeling diode and the H bridge. So if you still remember, when once you have learned on the power electronic, so this is quite related on the previous of the power electronic to control the to control the speed of the motor and something else. Okay, so if you know, okay, based on the first equation here, okay, for the first equation here, okay, if you still remember, this is the speed, the equation of the speed, which is equal to the Vt over the Kv minus to the Ra over to the Kv square times to the Td. So according to this equation, okay, for a given torque, the motor speed is a function of the following the three quantities, which is the armature resistance, okay, the value of Ra, the terminal voltage, which is the Vt, and the field flux. So according to this part, so hence the speed of the separately excited motor can be controlled by of these three. So if you still remember, so how to control the speed of the motor for the first, which is the adding of the armature resistance, and then the varying the terminal voltage, and then the adjusting the field flux. So on this part, okay, on this part we will more focus on the varying the terminal voltage. Okay. Okay, this is the solid state control of the separately excited DC motor. So, if you know, for the DC machine, they have two parts, which is the armature part and the field part. So the solid state converter is often used in the armature circuit to control the terminal voltage of the motor. So the converter circuit is placed on the armature part. So the converter also can control the speed of the to control the terminal voltage of the motor, which is can control the speed of the motor. And then in some cases, okay, in some cases, the converter is also used to control the field voltage, which is the another part, which is the field circuit. Okay, so what happened when a converter is used, the power source can be either or DC. So it depends on the power source. So according the normal condition, we use a AC source, and then to convert for then to if you want to use the DC motor, so we need to convert from the AC to DC using this converter. Okay, so but it also can be DC source also, but it's depend on the power source at the side. Okay, so the armature circuit of the motor in the figure 6.7 is connected to the solid state converter, which is fed from the AC source. So from the AC source here, okay, so from the AC source here, they will connect to the converter, and then converter will connect to the motor. So and then the field circuit motor is excited from the AC source, okay, AC source through the full wave rectifier circuit, which is may contain the filter. So yeah, so it is depend. Okay, so based on this one, okay, the full wave rectifier is connected at the field circuit through the AC source. Okay, so I think you can understand the solid state control of the separately excited DC motor. Okay. Okay, we move to the single phase half wave drive. Okay, for the single phase half wave drives. So according to the circuit, okay, if you still remember for the separately excited DC motor, so this is the complete circuit for this one, which is the thyristor is used as the switch, and then the terminal voltage VT can be expressed as VT is equal to the EA, okay, EA plus IARA and plus the LA DI per dt. So according to this one, the armature winding inductance LA is included because the armature current IA is not constant. Okay, so the LA is usually a lot of lower than the value of LF for the inductance for the field circuit. Okay, according to this one, okay, if you can imagine the switch, the operation of the switch, which is the ACR. So we have a two condition, which is the before triggering and then the during the ACR condition. Okay, so according to this graph here, okay, this waveform, okay, before the triggering of the SCR and A at the alpha, so so if no conduction, okay, before triggering no conduction, so the value of I is equal to 0, and then what happened to the value of the VT here, so which is the value of VT, and then this is the Vs, so Vs is sinusoidal, and then this is the value of Vt because the Vt is depend on the circuit of the operation. Okay, so before the triggering of the SCR at the A, which is the alpha here, okay, the current is equal to 0, so the terminal voltage Vt is equal to the EA. Okay, so we have the EA here, which is the value is 100 volt. Okay, and then during the SCR conduction, okay, during the SCR conduction, the VT is equal to the instantaneous source of voltage of the VS. So once the SCR is closed, okay, the SCR is closed, the switch is closed. So what happened? So the current, if it is, will be conducted, and then the value of the VT is equal to the value of the VS. So if you can see here, okay, you can see here the value of VT is same with the VS once the current is conducted. Okay, so the third one, the voltage across the resistive component. Okay, once the voltage across, which is the value of the resistive component of the armature winding, is identical in shape to the instantaneous armature current. Okay, so and then the B, the beta. Okay, once the beta is the angle at which the instantaneous current reach to its zero crossing. So what happened once the zero crossing, the beta is at the zero. So what happened to the value of VT? So is identical to the for the first one, which is the VT is equal to the IA. So this shape will continuous by referring to the SCR condition. Okay, so once the SCR is turned on again, so what happen is uh, it will operate like the previous. Okay, I hope you all of you can understand for this condition. Okay, during the steady state operation, so once the operation is in steady state condition, the field voltage Vf is kept constant and the motor speed is assumed to be fairly constant. Hence, the EA is also constant. Okay, the load current, okay, the load current of IA can be computed by the value I is equal to VT minus EA over the RA plus JXA. Okay, the current equation during the conduction period between alpha and beta can be expressed by, okay, the I is equal to the VT minus with the EA over the RA plus JXA, which is the equal to the impedance, which is Z. And then as you can remember, the previous of the voltage apply is equal to the Vmax sines omega t. So if we convert from this to the time domain, so we will get the equation 6.13. So according to this one, the phi is equal the tangent times to the omega LA over the RA, and then the tau is equal to LA RA, and then the value of Z is equal to square root RA square plus omega LA square. Okay, and then the omega is equal to pi f. So according this one, where Z is the impedance of the armature winding, phi the phase of angle of Z, t tau is equal to the time constant of Z, and then f is the frequency of the AC source. Okay. Okay, for the next one, which is the average voltage across the terminal of the motor. So the average voltage across to the terminal the average voltage across the terminal voltage of the motor can be expressed by the equation 6.16, which is the VT average is equal to EA plus with the BL average plus the I average RE. Okay, where the BL average is average voltage across the inductive element of the armature impedance, and the I average is the average the armature current. Since the VL average is 0, the equation 6.16 can be simplified to be like this. So the VL is equal to 0, so can be expressed can be simplified. The equation of the voltage terminal average is equal to EA plus I average RA. So I hope you can remember for this equation. Okay, VT average is equal to IA plus with the I average RA. So this is for the single phase half wave drive for the separately excited DC motor. Okay, the average voltage, okay, with average can be expanded as follows. Okay, the average voltage, so VT average is equal to the EA plus I average RA. So if we want to solve the equation for this one, so to get the value of the speed, so we need to integrate the value of the VT here. Okay, VT derivative 0 to 2 pi, so 2 pi, which is the full cycle, which is the 360 degree, and then the value of EA plus the RA to pi, the value of the ID omega t 0 to 2 pi, and then we need to separate for the alpha to beta. Okay, the alpha to beta, the conduction period, and then the beta to alpha plus 2 pi, which is the condition is before triggering the switch. Okay, VT d omega t, and then this is maintained, okay, from EA plus R plus RA over 2 pi, integration of I d omega t alpha to pi, and then we solve the for this one, the integration, and then the EA to pi plus alpha minus with the beta. And then for this one, we solve the value of EA plus RA I average. So according to this one, note that during the interval from A to alpha to beta, the VT is equal to the source voltage, and the beta and between the beta and triggering angle of of the next cycle, alpha to plus with the alpha plus 2 pi, and during this condition alpha plus 2 pi, the VT is equal to the AA. Okay. Okay, so this one, okay, the based on the previous equation, so we get the where the gamma is conducting period, which the gamma is equal to beta minus with the alpha, which is for example the conducting period from 60 degree to 150 degree. So the conducting period in 90 degree, so we replace with the gamma here. So according this one, we solve the value of Vmax here. Okay, Vmax sin the Vt d omega t, and then we replace the equation of the gamma. So we get this equation 6.18, and then replace with the EA. Okay, if you still remember, the EA is equal to the kV speed. Okay, so according to this one, we get the final equation, which is 6.19. So this is the final equation that you must have remember. Vmax is over to the 2 pi cos alpha minus to the cos beta is equal to gamma over 2 pi kV speed plus the RA average. So I want all of you please take note for this equation for 6.19. Okay, so based on this equation 6.19, how to get this value of the motor speed can be written as this one. So I want all of you try to get this the final equation where this the speed is moved to the left side, and this all equation put the right side. So we will get this final value. So the motor speed can be expressed for the half wave drive, for the single phase half wave drive, so can be written like this one. So I want all of you just remember the equation for the 6.19 to get this the final value of the motor speed. Okay, so we try together for the example to do exercise of the example one. So according to this one, we have a 1 horsepower decision motor. So I hope all of you still remember the basic circuit of the decision motor. So I want all of you try this one to make sure you understand uh, the the previous one of the half wave drive of half wave drive. So so I want all of you take note. Okay, please take note for this one. Okay, and and remember what is the parameter. Okay, the alpha, beta, and then the gamma. Okay, so according to this one, the loaded torque, which is 10 newton meter, and then the armature resistance of the motor is the 5 ohm, and then the field constant, the kV, is 2.5 voltage volt second, and then the motor is driven by a half wave SCR converter. The power source is 120 volt, which and the frequency is 60 hertz, and then the triggering angle of the converter is 60 degree. So the triggering angle, you must remember the triggering angle is a alpha. So the alpha is 60 degree, and then the conduction period is 150 degree. So means the conduction period is a this is a gamma, not a beta. Okay, this is a gamma. So if you want to get the value of the beta, so you need to uh, plus with the alpha and the gamma 60 plus with the 150 degree, and then you get the 210 the value of the beta, and then based on this one you need to calculate the motor speed and the developed power. So I want all of you remember the equation of 6.19. So to make sure all these thing you can do very well. Okay, so for the first thing first, I want all of you draw the basic circuit of the shunt DC motor, okay, including the parameter given, the parameters given. So the VS, which is 100 volt, 120 volts, and then the frequency is the 60 hertz, and then the triggering angle, which is the 60 hertz, which is the value of alpha, and then the value gamma, which is the conduction period, okay, the conduction period, which is 150 degree, and to get the value of beta, 60 plus 150 is equal to the 110, and then the value of kV is equal to 2.5 volt second. So according this equation 6.19, okay, this equation 6.19, the Vmax over 2 pi cos alpha is minus with times with the cos Vmax Vmax over 2 pi times with the for alpha minus with the cos beta is equal to gamma over the 2 pi kV speed plus RA times with the I average. So if you still remember the value, why according this one they give the value of the Vs, so we need to use the value of Vmax. So how we want to convert from the Vs? So Vs is uh, we need to times with the square root 2 to get the value of the Vmax. Okay, so because the value of Vs is equal to the value of Vpeak, so we need to times with the square root 2. Okay, so the first thing, okay, you need to find the average armature current. Okay, can be determined by the load torque and the motor excitation. I average is equal to the torque over the kV, and then the value I average. Okay, you must the first one you must remember what is the first step. You need to get the value I average, is which is the torque over the kV, 10 over 2.5. You can get the value 4m, and then just direct substitute from this parameter to equation 6.19, and then if I said before why we need to times with the times we need to times with the square root 2, because we need to find the value of Vmax. So the Vs equal to Vp, so we need to find the maximum value of the voltage. Need to times with the square root 2 times with 120, and then 2 pi cos to the alpha, and then minus to the cos beta. So the beta is the alpha plus with the conduction period, which is 150. So we get the value of the beta here, and then just replacing the gamma value, and then 2 pi. So the 2 pi is 600 degree, right? Okay, so that I said before, the 2 pi is 600 degree, and then times with the 2.5 plus the motor speed plus 5. Okay, 5 plus 4, which is the value of value of Ra and I average. So the motor speed, okay, so the motor speed in radian per second, yeah? So you need to convert from radian per second to the rpm, so you will get this value 145 uh, 154.18 the rpm, and then just replace to get the value of the developed power. The PD is equal to the EA average, so just replace the value of EA is equal to the kV speed, and then you will get the developed power 162 watt. Okay, so according to this one, so I hope all of you can understand. Okay, so 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 this is the developed power. Okay, so according this 1 horsepower motor, so which is 21% of the motor rating. So you need to convert first the horsepower to watt, and then you will get the percentage of the motor rating.